The last topic here is involving variation. And I'm going to show you a couple of different methods to solve variation problems. First, we'll see what a variation problem is. And then we're going to solve some variation problems. Today, we're going to work with two kinds of variation, direct and inverse variation. I'll explain what those are in just a minute. We want to solve direct variation problems using proportions, which you'll find to be wonderfully easy. We're going to solve direct variation problems using the constant of proportionality, which is almost as easy, but a lot more versatile. And then we're going to solve inverse variation problems. Now, first of all, a little bit of background. First of all, what is a direct proportion? Basically, it's this. You say that two things are directly proportional or that they vary directly if an increase in one results in a proportional increase in the other. Here's an example of that. Suppose you've got a steel beam. Okay, there's our steel beam. Wouldn't you say, I mean, without having any mathematical knowledge at all, wouldn't you say that in general, the longer that steel beam is, the heavier it's going to be? Okay? Well, then you would say that the weight is proportional to its length, or that they're directly related. We could say that its weight, and the symbol for a proportion is similar to the little alpha symbol here. So we would say that weight is proportional to length. That's a direct proportion. That's all there is to it. Okay? With that in mind, I'm going to give you two more things that are related, and I want you to tell me whether they are directly related or that they vary directly. First one, is the price to fill your tank with gas, is that directly proportional to the amount of gas that you pump into it? It is. Right. If somebody next to you pumps twice as much gas, it's going to cost them twice as much. Okay, those two are directly related, or we would say that the cost of the gas varies directly with the amount that you pump. Does that make sense? Okay. What about the second? Is the time needed to drive to Winona directly proportional to the speed that you drive to get there? No. What happens to the time to get to Winona if you drive faster? If you make your speed go up, what happens to the time to get there? It goes down. Those two are not directly related because an increase in your speed does not result in an increase in your time. It results in a decrease in your time. Those two would be said to be inversely proportional. We'll work with inverse proportions in a minute. Okay, well, there's two methods to solve any proportion problem. There's one method called the proportion method that's easier, but it's more limiting. You can only use it in certain circumstances. There's a second method called the K method, or the constant of proportionality, that is a little bit more work, but it works in many, many more circumstances. So let's take a look at this situation right here. We're going to solve this using a proportion. Let's say that the price of a cable is directly related to its length. That is to say, if you buy a cable that's twice as long, it's going to cost you twice as much. So let's say that a 25-foot cable costs $9.75. Then how much is a 60-foot cable going to cost? Now, one thing that you might be thinking is, we'll figure out the cost per foot. That's the K method, or the constant of proportionality method. We're going to do that later. What we're going to do right now is we're going to set up a proportion. What we'll do is we're going to say that the length of the first cable compared to the length of the second cable is equal to the cost of the first cable over the cost of the second cable. Directly proportional means that we're talking about one cable on the top half of this proportion and then the second cable on the bottom half. Well, then we fill in our solutions. The length of the first cable was 25 feet. The length of the second Nope. Ryan asked if it matters which one goes on top. Doesn't matter. As long as the only thing that does matter is that once you decide that the shorter cable's information is on the top, you have to put its length and the price on the top. You wouldn't want to put the shorter cable's length up here, but the shorter cable's price down here. So we have $9.75 for the 25-footer. We want to know how much for the 60-footer. You solved proportions before, cross multiply. Okay? So in this direction we have 975 times 60, and in the other direction we have C2 times 25. Divide both sides by 25. And what is the cost of the second cable? $23.40. So the second cable costs $23.40, and we're done. That's all there is to it. The cost of the cable, the length of the cable are directly proportional. Okay, here's another one. Now this is the same principle, but use the same idea. It's just that we're going to work with a different type of quantity in this case. Here's the situation. The pre-tax price of an item is directly proportional to the price including tax. That is to say, you pay the same sales tax rate regardless of how much the object costs. You always pay 5.5%. Here's what we want to know. What's the pre-tax price of a television if the total price is $411.40, including 5.5% sales tax? Now, you could have solved this problem back when we did percents, but let's treat it as a proportion problem. We're going to put the rate, I'm going to put N with no tax on it, the rate with no tax compared to the rate with tax. That's proportional to the price with no tax compared to the price with tax. Well, let's fill in our values. What do you have to pay for? If there was no tax, what percentage of the price would you have to pay? You would just have to pay for the TV, 100%. Okay, so the rate with no tax, we would say, is 100%. Do we know the price with no tax? No. What is the rate with tax? If we have to buy this thing, we pay for 100% of the price of the object plus what additionally? Plus another 5.5%. So the rate with tax is 105.5%. And the price with tax is $411.40. What's that, Drew? I'm paying 100% of the TV's price plus an additional 5.5% tax. So in other words, if you went out and bought a $100 MP3 player, I can't think of anything that costs about $100. Let's say a $100 MP3 player, the MP3 player is $100, but you're going to have to pay $105.50 with tax. Make sense? So then we're going to solve it just as we did before. So you can solve that proportion. And the price with no tax turns out to be, did anybody already crunch that out? $389.95, and we're done. Okay. Now, the constant of proportionality is basically a value that ties the two variables together. If we had two variables, x and y, that were directly related, like the ones that we've had so far, we would say that y is equal to k times x. And k is usually just a rate. So let's go back. And resolve the cable problem, but this time we're going to use the method of the constant of proportionality. And you might say, well, why would you want to use a different method when that one works so easily? Because the proportion method is actually going to be limiting. It only does a certain type of problem, and tomorrow we'll see why the K method is a little bit more flexible. Here's what we've got. Same problem we saw a minute ago. You already know what the answer is going to be. But let's resolve this. Here's the key. The price of the cable is directly related to its length. When you use the proportion of, or the constant of proportionality, you read the first sentence. Price of the cable directly related to its length. So we would say that the price of the cable is directly related to equals k times the length. that right there, equals K, is a way to represent is directly related to. Now, all we do is we take one case that we know, we plug it in to figure out what the value of K is that ties these two together. So, for example, we know that the 25-foot cable costs $9.75. So we say $9.75 equals K times 25 feet. Now, you want to solve this for K. You want to find out what the K value is, the number that ties these two things together. So solve that for K. What does it work out to be? 0.39? 0.39, or in other words, we get $39 per foot, or $0.39 per foot. So what does that tell you about this cable? 39 cents a foot. K is really just a rate that tells you how these two are changing together. If we were to buy a 1-foot cable, it would cost us 39 cents and so on. When you go on to take physics, you'll be working with various constant of proportionality values quite often. Now we can answer the question, how much will the 60-foot cable cost? Well, we go back to our original relationship. The price is going to be equal to the K value, which we now know, times the length. And in this case, that's 60 feet. And if you multiply those two together, you'll be shocked to learn that the price turns out to be $23.40, the same price we found the other way. We never set up a proportion. We found out what the rate is between those two, and then we went and solved it. Now, again, you've done that before. That's probably how half of you would have answered the question when I first showed it to you in the beginning. It's just putting it in mathematical terms. Springs on a truck compress a 1/4 inch for every 175 pounds you put in the back of the bed. And if you can safely compress the springs on that truck by 4.5 inches, then how much weight would it take to do that? How much weight can this thing haul to compress the springs 4.5 inches? Well, you certainly could set up a proportion. I'll trust that you could do that. Let's use the K method. Tell me, what is our relationship? What two things are directly related here? The number of inches the springs compress and the weight. All right? So let's say that our weight is equal to, or is directly proportional to, the amount that the spring compresses. The weight of the truck is, the weight of the load is directly proportional to how much the springs compress. Everybody agree with that? Let's make a note here that W is the weight, and C is the distance that they compress. Okay? Well, once you've got your relationship, now we just need to take one particular case that we know to figure out what the K value is, how those two are tied together. What circumstance do we know to be true? We know that it's a 1/4 inch for 175 pounds. So when our weight is 175 pounds, that's going to equal K times 1/4 inch, or 0.25 inches. Agree with that? Now we can find out what the K value is for these springs. Solve for K. $175 divided by 0.25 is 700, and your units are pounds per inch. Well, again, K is the rate. this thing will, or it takes 700 pounds to compress these springs 1 inch, or to make that pickup sag 1 inch. Now, we know that the springs can safely compress 4.5 inches, so how much weight is that? We go back to our original relationship. We want to know how much weight that'll take. So W is equal to our K value, 700 pounds per inch, times how much are we willing to compress them? 4.5 inches. And that works out to be 3,150 pounds. How about 1.5 tons? Suppose D varies directly with M, wham. If you read the first sentence, half the problem's given to you. All right. Suppose D varies directly with M. Right there, what relationship can you write right off the bat? Almost. D equals Km. D equals Km. I use capital M, right? Yep, D equals Km. So, there you go. If M equals 15.9 when D is 6.83 times 10 to the negative fourth. All right, so M equals 15.9 when D equals 6.83 times 10 to the negative fourth equals K times M, which we know to be 15.9. Now we can solve for K. Okay, we can find out what our constant of proportionality is. And if you do that, K is going to turn out to be around 4.296 times 10 to the negative fifth. We got our constant of proportionality. No units on this one. Okay? Anybody else get the same thing? Verify that that's right? Yeah, okay. So we got our constant of proportionality. Now we want to find M when D equals 2.57 times 10 to the negative second. So we're going to use our original relationship here. D equals 2.57 times 10 to the negative second. That equals our K value of 4.296 times 10 to the negative fifth times M. Well, you can solve for M with very little trouble. Divide both sides by K. We could have done that up here. .57, that's our value of D, times 10 to the negative second, divided by K value. M turns out to be, anybody get that? 598. Keeping with 3 significant digits, our values there are given with 3 sig gigs, so we keep 3 sig gigs. So M is 598, and we're done. We found the value of M.
So it wouldn't even matter which one we're solving for.
Okay, let's do one more, and then we're going to move on to inverse variation. We want to finish off this table, and we're going to assume that A and B vary directly. Okay, well, which column are you relying on there? There's actually 2 problems. There's 2 problems in there. One is find the B value that goes with A when it's 4.73. The other one is find the A value that goes with a B value of 9.62. And what is this good for? You're told both of them, so we don't have to do anything? Yeah, you use these 2 to find out what your K value is that ties them together. So we know that A is directly proportional to B, and incidentally, we could set up a proportion and solve this, but we're going to get in the habit of using K. A is equal to K times B, and so we know that 2.55, from the one case that we're given, 2.55 is equal to K times 8.37. Solving for K, we find that K is equal to 0.3047. Now, just a note of caution when you find your K value. The K value is often a long repeating decimal if things don't divide out nicely. How many sig digs should you keep? Well, on all the input values, we were given 3. So you'd want to make sure that your K value, so that you don't get rounding error, contains at least 4. Always leave your K value sig digs more than your input and output value so you don't get rounding error. So in this case, K is 0.3047. Okay, well, to solve this first column over here, A is equal to K times B, so we can say our A value of 4.73 is equal to our K value, which is 0.3047 times B. And if you do that, B will turn out to be 15.5. Look okay? And the second one up here, we know that our A value will be given by our K value, 0.3047, times our B value of 9.62. And A turns out to be 2.93. And we're done. We filled it out. All right, well, inverse variation. If direct variation is like an elevator, where both quantities are in the elevator, one goes up, the other one goes up, inverse variation is like a seesaw. One goes up, the other goes down. Two things are said to be inversely related if their product is constant. That is to say, if you multiply the two things together, you always get a constant value. In general, it just means that an increase in one quantity results in a proportional decrease in the other. The time needed to get there is inversely proportional to the speed of the vehicle, assuming you do not get pulled over. So if you double the speed at which you drive to Winona, what's that going to do to the amount of time it takes to get there? It's going to take you half as long. If you drive 1/3 as fast to get there, it's going to take you 3 times as long. And so we say that the time varies inversely with the speed. That's one example. Here's a couple more. The weight of a bowling ball. Is there any bowlers in here? Bowling is great. But in general, the weight of a ball is inversely proportional to the speed at which you can roll that thing. That's why you go and, if you want to be really macho, you go get one of the 6-pound kiddie balls, right? Because then you wind up and you give that thing a roll and it flies down there. In general, if you use a ball that weighs half as much, you're going to be able to throw it twice as fast. Okay? There are other factors in that, but the relationship is generally true. And so the weight varies inversely with the speed at which you can roll the ball. There's another example. So we can use proportions to solve inverse variation problems also, but you need to make one switch. We're going to solve this problem twice. We're going to solve it once using a proportion, and then we're going to solve it again using the K method. So here's an example. If you have a constant voltage, current through a circuit varies inversely with the resistance. That is to say, if you increase the resistance, it's going to decrease the amount of current. So here's what we need to draw from the first one. What we can say from that first one is, if we want to use a proportion for this, we can say that the resistance in the first circuit compared to the resistance in the second circuit is equal to, now, here's the switch. If we are talking about an inverse proportion, where if one goes up, the other goes down, we have to switch the proportion. So we don't put, if this is the resistance of the first circuit, we don't put the current in the first circuit up here. We put it down here. So this would be the, I know that the symbol for current is I, but I'm going to write C. The current of the first one compared to the current of the second one. In an inverse variation problem, the two things are related diagonally. So let's fill in our values. Our first resistance, we know that the current is 255 when the resistance is 470. So our first resistance is 470 ohms. That corresponds, now it's an inverse, so we don't go directly across, we go diagonally. That corresponds with a current of 255 milliamps. .470 ohms corresponds with a current of 255 milliamps, so we want to know what the resistance is. We'll call that our second resistance when, I wrote that wrong. We want to know what the second current is when our resistance is 220 ohms. The key is that it's inversely proportional, so that these two are related together and these two, they're related diagonally. Well, then you would solve it just as you did before. And our second current turns out to be anybody get that? 545. That's right. It turns out to be 545 milliamps. Now note, the original values given, the first sentence up there, or the second sentence was, it was 255 milliamps when the resistance is 470. We decreased the resistance down to 220. What happened to the current? It went up. Okay, so decreasing the resistance meant that we increased the current. Inverse relationship. One goes down, the other goes up. We're going to solve the same problem, but now we're going to use the K method. That look okay? Okay. Same problem, now we're going to use the K method. This time, we know that these two are inversely related. So here's what we've got to write. We would write the current is inversely proportional. So we say that it's K times 1 over the resistance. We take the reciprocal of the second one if they're inversely related. That's why we take the reciprocal of the second half of the proportion. Or, more simply, we just write C is equal to K, not times R anymore, but divided by R. And that's our new relationship. Now everything else we do is the same. So let's take the one case that we do know. We know that the current is 255 milliamps equals K divided by, and we know that that's true when the resistance is 470 ohms. That's the one case that we know to be true. Now we can solve for K. Multiply both sides by 470. And K is equal to, where'd it go? 119. 850. Your units are milliamps per ohm. Now, just for those of you who are in the electronics program, what is K representing here? If you take your resistance, whoops, I left the units off of that. If you take your resistance and multiply it by your current, though we'd have to put it in amps, what do you get? You get volts. Here, K is basically your voltage, except for we're leaving it in milliamps, so it'd be in millivolts. So K is just, the constant of proportionality for this is Ohm's law. And our constant of proportionality is just the voltage. That's really what we're doing in millivolts. Okay, well, once we know K, now we can go back and answer the question. We want to find out what the current is, so find C. C is equal to our K value, 119,850 milliamps per ohm, when the resistance is 220 ohms. K divided by R. And if you divide that out, you end up with the same result, 545 milliamps.
So that's also called the inverse portion.
Okay, let's do one more. Actually, just a couple more here. Suppose G varies inversely with H. Well, there's your equation. The first sentence tells you to write on your paper what? G equals K over H. G varies inversely with H. There it is. So if G equals 6.75 times 10 to the negative fourth, when H equals 982, okay, there's enough to find K. We get a K value of 0.66285. And that's equal to K. Okay? All right, well, if that's our K value, then we can solve. Find the value of G when H equals 1630. So then find the value of G, that's K, 0.66285. When H is equal to 1,630. What does G turn out to be here? 4.0, does it round up to 7? Times 10 to the negative fourth, and we found G. Here again, H went up. It went from 982 to 1630. What happened to G? It went down from 6.75 times 10 to the negative fourth down to 4.07 times 10 to the negative fourth. Inversely related. Okay. What we want to do here is we want to figure out how these two change, even though we're not given values of A and B. Suppose A varies inversely with B. So A equals K over B. If B is tripled, what's the corresponding change in A? Now, you might be able to answer that without doing any math. If these are inversely related, one goes up, the other goes down. If we triple B, what's going to happen to A? It's going to be 1/3 of A, right? Okay. A is going to be 1/3 of its original value. Well, we can solve this using proportions. We can solve it using the K method. Let's use a proportion in this case. Now, it's inversely related, so we would say that the first A value compared to the second A value is equal to what? We're not using the K method here. We're going to use a proportion. Since it's inverse, what's this going to be? B2 over B1. Right. That's because it's inverse, so we switch two of them. There, A1 is related to B1 diagonally, and A2 is related to B2 diagonally. And what's the other fact that we know? B is tripled, so our second B value Well, it could be the first one, but we're just saying that the first value is B, and we're going to say that the second one is 3 times the first one. So the second B value is 3 times the first one. We're going to let this change. We're going to take our original B value and triple it. Does that make sense? Well, then we're going to substitute back in here. A1 over A2 is equal to B2, which we now know to be 3B1, so we substitute 3 times B1 over B1. Okay, well, does that look all right? It's based on the fact that our second B value is 3 times the first B value, so we just make that substitution. What happens to your B1s? They cancel off, and we're left with this fact. We're left with the fact that A1 over A2 equals 3. Well, we want to know how these two are related, so if we multiply both sides by A2, we can say that A1 equals 3 times A2. But we want to know how the second one changed. We want to know that the second A value is 1/3 of the first A value. We divide both sides by 3, and that's the fact that we want. Our new A value will be 1/3 of the original. That answers the question. Okay, let's do one more. Last one. Heat loss. You know what R value is? For insulation, R value is a rating of the resistance to heat flow. So in your walls, you put insulation that's got an R value. And the higher the R value, the better it insulates. So a typical R value for a wall, insulation is around 11 or 13. And your ceilings, you want more insulation value because that's where most of your heat goes, and that R value can be 20 or 30 or 40. In general, the higher your R value, the lower your heat loss. So heat loss and R value are inversely related. If we take the windows out of this room, the R value of those windows will be 0, and our heat loss will be phenomenal. Heat loss will go way up if the R value disappears. What we want to do is we want to find out what happens to your heat loss if you increase the R value of your walls or any other thing by 20%. We're going to use the same method we did before. We know that we'll call H our heat loss. So our original heat loss compared to our new heat loss. Now these two are inversely related, so our R value is going to be reciprocal. We're going to take the reciprocal of that. So our original heat loss and our original R value are related diagonally, and our new heat loss and our new R value are related diagonally. Okay? Well, what's the second thing that you're told? You're going to increase your R value by 20%. So kind of like before, our new R value, R2, is going to be in what in relation to R1? It's going to be what? 20% greater. How do you write a 20% increase? 120%, or in other words, 1.20 R1. That's 120%. Our new R value is 1.2, or the original R value plus another 20% of the original R value. Substitute. H1 over H2 is equal to, let's see, we know what R2 is. It's 1.20 R1 over R1. What happens to the R1s? They're gone. And we want to solve this for H2, the new heat value. So we have H1 over H2 equals 1.20. Or in other words, H2 is equal to 1 over 1.20 times H1. Stop there for a minute. All I really want to do is I want to know what the new heat loss is. That's what the question was. I want to find the new heat loss. So I'm looking for H2. I've got H1 over H2 equals 1.20. Multiply both sides by H2. Whoops, these canceled off, sorry. And so with that, I can divide both sides by 1.20, and I get H2 equals 1 over 1.20 H1. Now, what's 1 over 1.20? Let's just divide that out. H2 equals 0.833 times H1. Or in other words, our new heat loss is only H1. So our heat loss went down. Our R value went up, our heat loss went down. How much did it decrease? It decreased by about 16.7%. So our heat loss is only 83% of what it used to be. It's more efficient, less heat loss, and we're done. That's a 16.7% decrease. We're going to do more of these type of problems tomorrow. This is where we're going to pick up tomorrow. We're going to do more of these types of variation problems.